The last video talked about non-conservative work and what to do with that. I want to follow up just a little bit and talk about work in general. When we have a force that's applied over a distance, we can have some amount of work. If I apply a force this way, because I'm pushing this thing, and I apply a force over some distance, I'm going to do work. Now that's not the only force that's acting on this box. If I have this box sitting here, I have a gravitational force, I have a normal force, and I have this applied force. I can set up my axis and draw a box around this thing and have my free body diagram. Now I can say that the work done by my applied force, call this thing force A, work by force A, is going to be force A times the distance, and that's just fine because they point in the same direction. I'm moving to the right, my force is to the right. Remember, my work is my parallel force times my distance. It's all parallel already. I have another non-conservative force, normal force. The work done by my normal force I can calculate. Now, normal force is a non-conservative force because I can't write a potential energy function that goes with it. So normal force is non-conservative. I need the parallel component of my normal force times my distance. My normal force, so my displacement, at any point I'm moving directly to the right, my normal force is directly upward. Those are perpendicular. There is no parallel component. Even though I have this non-conservative force acting, and I have that non-conservative force the entire way. Even though I have this non-conservative force acting, the work that it does is zero because it's perpendicular. And it has to be perpendicular because that's what normal even means. I also have the work done by gravity. The work done by gravity, the force that I've got is mg. The distance that I've got, displacement, is d, but I need the parallel component of mg. And again, I'm saying parallel to my displacement. I'm moving to the right, mg points down. There is no parallel component. Gravity does no work here. If I had my same box, and I were moving it, even just letting it slide down a hill. So let me throw some friction in here. Kinetic. I would draw my forces, right? I'm going to have an mg. I'm going to have a normal force. And I'm going to have a frictional force. If I move this box from this location and let it slide some distance d down the ramp, the work done by my normal force is going to be zero because these are perpendicular. The work done by gravity, I would have to split my gravity vector into components. I'd have to have an angle for my ramp. So angle, this side is an mg cos theta, this side is an mg sine theta, not a big deal. The work done by gravity is going to be equal to, let me move this thing a little bit. It's going to be equal to the parallel component to my displacement. My displacement is going to be down the ramp. My parallel component is this guy. So I'm going to get an mg sine theta times d. The work done by friction, my normal force and mg cos theta have to be equal because otherwise I am sinking into my ramp or floating off of it. which means my frictional force up here is going to be mu k mg cos theta. The work done by friction is the frictional force mu k mg cos theta times the distance, but my force points to the left, my displacement points to the right, so I'm going to get a minus sign. This force, this frictional force, is trying to keep me from going down the hill, but I'm moving down the hill anyway. If the force is not getting what it wants, then it must be doing negative work. So I can find the work done by any force, whether it's conservative, like gravity, non-conservative, like friction, this one is non-conservative, but no work, because it's perpendicular. I can find the work done by any force. I don't have to limit myself to just non-conservative.